topics that go often side by side are wide area networks and troubleshooting. So grab some popcorn or a snack, plan on spending about 30 minutes with me as we troubleshoot point-to-point protocol, HDLC, and frame relay. As a side note, it'll be a good refresher for point-to-multipoint subinterfaces, point-to-point subinterfaces, what the commands are to make that successful, and we'll also include some layer 3 troubleshooting and routing as well. I'm excited to share this with you. I appreciate the time. Let's get started. Here's our playground for this troubleshooting wide area network lab. I've got R1 as our hub, and then R2, R3, R4, R5, R6, and R7 as remote spokes. The clouds represent frame relay, and these serial lines represent a point-to-point leased line connection. We can also assume for this troubleshooting exercise that everything on R1 is correctly configured as the headquarters site. It's something either in the network or at the remote sites that is causing our problems. So let's start off with our link between R1 up to R2. We can troubleshoot this by simply using these sets of commands. These two, or these three in the middle here, would be specific for frame relay. But basically, these questions say, is it us? Can we communicate with the wide area network? And then for frame relay, we're identifying whether or not our PVCs are solid and mapped correctly. And if they are, the show IP route will show us whether or not we have routes to the remote sites. And that would be going through the router. So also for this demonstration, R2, R3, R4, R5, and 6 and 7, they all have a network behind them, which is the 444 network for R4, the 333 network for R3, the 555 network for R5, and so forth. And we're using EIGRP as our routing protocol. And the goal is to get full connectivity from every device, from every network to every other network. So on R1, let's start off by trying a ping and see if we can ping this IP address of 146. So that's pretty straightforward. We'll do a ping and 23.1.2.146. So there was our ping to 2.1.2.146, and it is not happy. So let's start our troubleshooting. What do we check first? First thing I'd check is let's see if the interface is actually even up on R1. We'll do a show interface serial 0/0. I'll put the mouse right here and just let's see if it's up. Now this says that serial 00 is up, so it's not administratively shut down, but line protocol is down. So something about layer 2 isn't too happy. It's also using encapsulation point-to-point protocol. Well, let's go check the other side of that link. Maybe the other side isn't up. So we'll go up to R2 and we'll do a show. I'll put my mouse right here where we're looking so you can look at it and see. So we'll do a show interface serial 0/0, and I don't have that many modules, 0/0, and we can verify that we are using encapsulation PPP up here on R2, and check this out. We are administratively shut down. That would explain why we're not talking too well. So we'll fix that. We'll do a no shutdown command. And if everything else is okay, we should have an EIGRP neighborship, which also helps to confirm that we have full connectivity. So R1, we could try to ping now to the 2.2.2 network, specifically to 2.2.2.2. And if that works, then we know that we're good for that link. Okay, so PPP, that one's working. Let's go to serial 01 and see if we can get to R3. So the very first thing we do is do a ping. If it works, we got no more troubleshooting to do. And the IP address of R3 is 150. So we try that ping, and sure enough, that's not working. So let's take a look at the details of serial 0/1 on R1. We'll do that with a real quick show interface for serial 0/1. And it says that our encapsulation is HDLC. We're not shut down. Layer 1 is up, and it looks like layer 2 is having a problem. Now, if I didn't know if I had a cable connected or not, I could do a show controllers serial 0/1, and that would show me the type of cable that's connected and whether there's clock rate present. I happen to lab this up myself, so I know there's a clock rate present, and I also know there's a cable attached. So let's go check R3 on the far side. So we'll put R3 right here. We'll do a show interface for serial 0/0. And wow, it's not administratively shut down, but it also has a problem with layer 2. And this guy thinks that encapsulation should be point-to-point protocol. Now, the router 1 thinks it should be HDLC, and if it's If that's what we decided to do, HDLC, it's a misconfiguration issue over on R3. So let's change R3 to match R1, and we'll simply go into interface serial 0/0, and we'll say encapsulation HDLC. We could also say no encapsulation because it would default to HDLC. Now, assuming everything else is working and there's clocking present on both sides and they're both happy, we should be able to get a neighborship if everything's working correctly. So the link just came up. That's great. And our neighborship also just came up. So that is also working. So if we go back to R1, let's just verify that we can ping the networks behind R3. And that specifically is the IP address that's up, which is 3.3.3.3. If that works, great. Layers 1, 2, and 3, happy. That's PPP up here and HDLC right here. Now let's tackle frame relay, the puffy clouds. Now down here we have what's called a non-broadcast multi-access network. Woohoo, that's fancy words. What does that mean? Well, non-broadcast means this, that we don't have a pipe, a PVC, a permanent virtual circuit between every device. See, R5, if he sends a routing update, guess what? R4 is not going to hear that directly. Why? Because there's no blue PVC, permanent virtual circuit, between R5 and R4. So that's the non-broadcast aspect of frame relay. The second thing is we have at least 3 devices on this one subnet. And that's a non-broadcast, meaning we don't have a full mesh, multi-access, meaning we have at least 3 devices on this one common IP network. That's it. So non-broadcast, multi-access. So R5 and R4 and R1 are all there. Let's just verify that we can ping from R1 to R4 and R4 to R1. Now, on-ramps are, as you know, in frame relay are called data link connection identifiers. So we have this one permanent virtual circuit being provided by this frame relay service provider, and R1 recognizes this PVC as HDLC 104, and R4 recognizes the exact same PVC, but from R4's perspective, as 401. Why those numbers? Because that's what the frame relay service provider gave us to work with. So we're talking about one permanent virtual circuit, and we're identifying it locally by whatever number the service provider gave us. It's like 2 ends of a hose. The same hose, 2 different labels at each end. So let's see if we can ping from R1 to R4. We're at R1 already. Let's do a ping over to 23.1.2.130. And sure enough, that is not working. Big surprise. Well, what do? Well, we can make sure that our interface is up, make sure that we have a cable attached and clocking is present, and then we can verify that LMI is correctly functioning. What is that? LMI is an acronym for the Local Management Interface. Now, if you go over to a router and you say, well, show me the interface, there's no physical interface. The Local Management Interface is the set of protocols, the communication, the language of love, if you will, between your frame relay service provider's frame relay switch, which is represented by this big cloud, and your router. So we send inquiry messages, the switch sends a status and information back and forth about every 10 seconds. We have a little message that goes back and forth, and that is our LMI, our local management interface, as we communicate back and forth with the frame relay service provider switch. So let's see if that is working. We can do a show frame relay LMI, and that, well, I guess we can do a show interface first. Let's just do a show interface and make sure that serial 0/2 is up. Because if it isn't up, it's over. So serial 0/2 is up, line protocol is up, great news. And we have encapsulation of frame relay. So fantastic. While we're here, let's check the IP address. It's 23.1.2.129 with a /29-bit mask, which is perfect for the .128 subnet. So let's find out what's going on. Let's go ahead and do a show frame relay LMI. That says, am I able to communicate with this frame relay switch? Because we're connected to the switch, they're connected to this frame relay switch, and it's the frame relay switch, the service provider, who's moving our frames back and forth in between. So it appears that we are sending inquiry messages and getting status messages, and we haven't lost any. So if we had timeouts down here, that would be a big problem, but it seems like the LMI is perfect. So LMI is working, so we can move down to the next one. Let's make sure we have the PVC called 104. To see that, we do a show frame, and PVC. Now, specifically, if you want to see all the PVCs, you can just press enter, but let's just take a look at PVC 104. So this is the details for PVC 104, and it says, great, it's being used, it's active, that's always positive, and it's assigned to serial 0/2, which is right here. Well, that looks great. Looks like the PVC is working fine. So why can't we send our packets over there? Well, let's take a look at our map. Let's do a show frame map. And the show frame map is going to tell us what our router believes it can use, which DLC it can use to reach this remote device. Frame relay maps are all about what local DLC do I use to reach a remote IP address. So router 1 should use DLC 104 to reach R4 at .130, and it should use 105 to reach 131, which is R5. So frame relay maps are mapping a local DLC because that's the only DLC we know. R1 has no clue about the DLCs on the far end. It only knows about its local DLCs. We're mapping local DLCs to remote IP addresses. So let's take a look at the maps, and that's this command right here. Show frame relay map. And I'll spell that correctly. Wow, it even took it. That's weird. All right, so show frame relay map right here. It says that our belief system, this router's belief system, is that to get to the IP address of 23.1.2.130, which is our good buddy R4, go ahead and use the local DLC 104. If you put an analyzer on the actual CSU, DSU, and you looked at it, that would be hexadecimal for that. Although I'm not sure how that all matches up exactly. It doesn't really matter. This mapping was created statically. So on the router, we actually configured a frame relay map statement. It wasn't learned dynamically. And we added the broadcast keyword so our routing protocols would work. So that part looks perfect. Absolutely great. I also did mention, however, that everything on R1 is perfectly configured. So let's go take a look at R4. Maybe we could send the ping, but R4 couldn't get back to us. Let's go over to R4, and R4 looks like he's having an EIGRP nightmare. Well, let's do these commands again real quick. Let's make sure that the interface is up. Show interface serial 0/0, and I'll point to it right here so you know exactly where we're at. All right, so it looks like the interface is up. And you could also do a show IP interface brief, but it wouldn't give you the encapsulation and stuff that you need to see. The encapsulation is frame relay. That part looks good. And check it out. Right here, even without doing show frame LMI, it's showing us that we have this many inquiries sent and this many received. And that looks like LMI is absolutely fine. So LMI is working perfectly. We don't even need to do show frame LMI because we see the numbers right here. Let's take a look at the PVC 401. Let's do show frame PVC. And let me just bring it up 2 pages. So this is the command issued, show frame PVC. It's showing us 2 PVCs. On our diagram, I only see 1, but let's take a look. It says DLC 401 is identifying a PVC. It's active, and it's assigned to serial 00. Well, that part looks all great. It also shows us a DLC 444, which I don't see on our diagram, and it says the status is deleted. That's bad news. Here's what that means. It means R4 in its configuration, it's trying to use a PVC called 444, but the LMI that's chatting back and forth with R4 from the frame relay switch, the frame relay switch is saying over and over again, hey, you got DLC 401. That's it. And because DLC 444 doesn't really exist from the frame relay switch's perspective, and it's not being reported via LMI, the router is going to show it as deleted. That's what that means. It means your local router is trying to use a PVC, a DLC identified PVC that the frame relay switch simply isn't providing to that device. So that's what that means. Now, what's our next step? Let's take a look at our maps. Let's see how R4 believes which DLC it should use to reach the headquarter router of .129. And that's this command right here. Show frame map. And there we, this is not good. This is R4 saying, I believe, based on the static mapping that's configured on my interface, I believe that to get to this IP address, which is R1's IP address, I should be using DLC 444, which, by the way, the switch, the frame relay switch, doesn't have. It's not configured. It doesn't exist. And that's the reason R4 can't ping. We have an incorrect map statement. So we'd want to go ahead and take that out. So an interface serial, and we're on R4. So an interface serial 0/0. We'd want to do I'm just going to show you the command real quick. Do show run interface for interface serial 0/0, and please exclude anything that has the word clock in it. So there's the interface serial 00, and there's our incorrect map. So I'm going to take it out just by highlighting it, pasting it in, and then I'm going to put in the correct map. Frame relay map, to get to the IP address of headquarters, which is 23.1.2.129, please use DELC 401, because that's the DELC you have. We could also learn this dynamically through inverse ARP. Inverse ARP, if I gave it 60 or so seconds, would dynamically get that mapping. And if I did let it learn it through inverse ARP, it would also add the keyword broadcast by default. I'm going to manually put this in because I want to show it to you. And the broadcast keyword is so that routing updates that R4 feels he needs to send out this interface can be sent down DELC 401. This is for multicast broadcast updates that routing protocols need to generate. If I don't put it on there, the routing updates for EIGRP would not be sent down, and R1 wouldn't learn about the 444 network behind R4. So now that's done, let's try our ping. So we'll go down to R1. R1, this is a very good sign, by the way. We got an adjacency with EIGRP. That means that we can talk to him. We'll do a ping over to, get my history out here, to 130, and that works. And if we do a ping to 4.4.4.4, that also implies that we can get to these networks that are being advertised via EIGRP. All right, man, we're doing great. We're half the network done. Let's go take a look at R5. Can we ping R5? Maybe we can. Maybe we'll get lucky. That is .131. So now we're trying to ping from R1 to 131. Should be using DELC 105 to get there. It's not happening. Let's take a look. We know the interface is good because we already checked that. We know LMI is good. Let's check the PVC of 105. And here it is. So here's the PVC. Looks solid. It's active. We're assigning it. It's assigned to serial 0/2. Let's check our maps. Show frame relay map. Press enter. And here's our mapping for 131 right here. And this also looks good. From R1's perspective, to get to the .131 address, use DELC 105. It's statically configured, not dynamically learned, and the broadcast keyword was added, so routing will work across it as well. Let's go take a look at R5 and see what its problem is. What are the steps again? Let's do a show interface serial 0/0. Now this is a sub interface, and because it's a sub interface, it has to be, because there's 3 devices on this network, it's got to be a multi-point sub interface, not like a point-to-point sub interface over here. So this sub interface, let's check the major interface and make sure the major interface is up and up, which it is. And we also have LMI that's working like a champ. So that rules out LMI not working. Let's go ahead and check out the show frame PVC. And that tells us that we've got one PVC identified as data link connection identifier 501. That's terrific. It says it's active, which is super also. We know what deleted means. Now active is a good sign. And it's also assigned to serial 00. Look at this. We need, just like on router on a stick, where you're assigning sub interfaces to specific PVC or specific VLANs, we need to do a similar concept with sub interfaces. This sub interface, if it's a multi-point sub interface, we would identify that this sub interface gets that PVC by using a frame relay map statement there. If this was a point-to-point sub interface, like over here, we would use the frame relay interface DELC statement. So let's check out our mappings over here on R5. Wow, look at that, nothing. This router has no clue on how to reach any layer 3 IP addresses via any PVC, let alone this one. So to correct this, we need to add a couple, at least one frame relay map. So let's go into configuration mode for serial 0/0.1. It is a point to multi-point sub interface. We can verify that with a do show run interface serial 0/0.1. When we first create the sub interface, it forces us to specify, is it point to point or multi-point? I need to know, it says. Then after it's created, you can just type in interface serial 0/0.1. it goes to that interface. It knows if it's point-to-point or multi-point based on configuring it earlier. So here's the IP address. We'll check that out while we're here, .131, which is correct, with a /29-bit mask in decimal. That's what that looks like. So that part looks good. What we don't have here is the frame relay maps. So if we go up, if we want to fix that, let's just do a frame map for IP. See, we can support a lot of layer 3 protocols on top of frame relay. Frame relay is a layer 2 technology. So in this case, we're just going to support IP. So Mr. R5 to reach the IP address of 23.1.2.129, which is our headquarters site, we want to go ahead and use HDLC number 501. It's an on-ramp. And in case we have any routing updates to send, we want to be able to send them down this PVC as well. Done deal. Now if we do a show frame relay map, it's going to show us that we have a static mapping configured. We know how to reach 23.1.2.129. But you know what, I was just going to say, I don't see the neighborship coming up, so we may still have a problem. Because the neighborship came up, that it's a strong indication that everything's good. Let's go back to R1 and test. So on R1, we'll do a ping to 131. It works. And let's also do a ping to 5.5.5.5, which represents a network behind R5. So fantastic. We've got this end of our network done. Let's head over to R6 and R7. Thanks for hanging in there with me. This is a good exercise and a good review of how frame relay operates as well as how to troubleshoot it. So on R1, let's try to ping R6. So the IP address over there is 142. This is also a good exercise, by the way, on variable length masking. If you look at this network, we basically carved up one chunk of networks and made it all fit. Here's a multi-access network, and all the rest are point-to-point with /30s. So that ping works, and that's no problem there. 23.1.2.142, that seems to be great. Let's see if we can ping 6.6.6.6. Okay, so we have our frame relay working here, but what isn't working is we don't have a route out to the 6 network space, which is over here behind our 6. So frame relay is all working great because we have connectivity with ICMP pinging. So let's take a look at our routing table and see why we can't reach the 666 network. I should probably change that. In any event, let's take a look. Show IP route. Let's just take a look at the EIGRP learned routes. And there's the 2 network, the 3 networks, the 4 networks, the 5 networks, and sure enough, no 6. Well, what would cause that? Let's do a show IP EIGRP neighbor. And there's all our neighbors. And these are the neighbors R2, R3, R4, R5. But we don't have, who's this guy right here? 146. Oh yeah, that's R2. So we have these 4, but we don't have R6. What would cause that? Let's see if we are running EIGRP on this interface. Always check at home first. Make sure your stuff is in order before you go looking at the remote. So how would we verify that this interface is participating in EIGRP? Show IP interface EIGRP. Show IP EIGRP interface. That would do it. And so this shows us that 2.6 is. So I don't even need to do a show IP protocols. I mean, I don't have to look at the network statements or anything. I know that this router believes that that interface is participating in EIGRP. So why can't we get routes from R6? Let's go ask R6 that same question. So show IP EIGRP interface. And wow, this says that EIGRP is running on serial 00. And we have connectivity to the router 1 interface. Perplexing. So let's look a little deeper. Let's do a show IP protocols and open the kimono a little bit. It's running EIGRP and has network statements in place for the 6 network and the 23 network. But why isn't it having any neighbors? Show IP EIGRP neighbors. Nothing. I got, oh, look at that. Here's the autonomous system number is 2. And on the rest of the network, I'm using EIGRP 1. So I've got the wrong autonomous system number on R6. So we'll fix it. No router EIGRP 2. No router EIGRP 2. and router EIGRP2. Oh, if I could just type 2. And I'm putting it back in. Oh my goodness. I'm going to leave the camera running. So I'll say no router EIGRP2. Router EIGRP1. No auto summary. And network. Check this out. Here's a shortcut. Network 0000 is a shortcut that says, hey, any interface that has an IP address, you're in. And as a result, show IP EIGRP interface. It's going to show us that those interfaces are involved, and we have a neighbor, which means now, because we're neighboring with R1, we're looking at the routes beyond the actual frame relay connection. So R1 should be able to ping the 666 network hiding behind R6. To verify that, we'll just do a quick ping. And sure enough, it works. All right, last leg of our journey here, or it seems, is R1 to R7. Okay, let's take a look at R7. We know R1's okay, because everything on R1, as I mentioned, is fine. So let's go over to R7 and take a look. Show, I'm going to mix it up a little bit. Show IP interface brief. It's a really quick way to verify that the interfaces are up or down. And look at this. Ooh, the sub interface is down doobie do down down. And that's interesting. So what could cause that? We know it's frame relay. I mean, we know it's encapsulated frame relay because it let us create the sub interface. So on the physical interface, we'd say no shut, which we did, encapsulation frame relay, which we did, and serial 0.1 is a point-to-point sub interface. Let's take a look at the config for that. Show run interface. Well, let's not cheat. Let's go ahead and do the steps in order. Is frame relay working? Let's verify. Show frame LMI. And that says, wow, sure enough, you're sending and receiving LMI messages. That part looks good. Do we know about the PVC called 701? Let's see. Show frame PVC. Sure enough, there's 701, and it's assigned to serial 00. Whoa, we've seen this before. We're using a sub interface, but yet the frame relay, the configuration believes that this PVC is going to be managed by the physical interface. So over here in a multi-point sub interface, we used a frame relay map to tell this interface that it belongs with DELC 501. In a point-to-point sub interface, we use the frame relay interface DELC statement, and it looks like it's missing here. So let's just do a show. The next step is a show frame map. And sure enough, it has no mappings whatsoever, which means it's missing the frame relay interface DELC statement. And we need to add it. So let's add it. Frame relay interface DELC statement, and that's going to be DELC 701. It's like saying, dear Mr. Router, this sub interface gets to pay attention to DELC 701. And now it has a home. So otherwise, all the DELCs by default are associated with the physical interfaces until you use a frame relay map statement to pull it down to a sub interface that's point to multi-point, or the frame relay interface DELC statement to pull it down to a point-to-point sub interface. And the neighborship came up. That's great. All right. So because that came up, I have high hopes we're going to have good success here. So we'll do a ping. Ping over to 7.7.7.7. And sure enough, so we've got full connectivity. So from R1's perspective, he's got all the routes. We think we're done. But there's one last challenge, which is normally one of the tougher ones for most people to identify and troubleshoot. And that is, in doing some random ping testing, R2 can ping R6 and R3 can ping R7. But we discovered that R4, let's go to R4 and do a show IP route right here. With the show IP route on R4, take a look at the networks we know how to reach. We know how to reach virtually everything, including a lot of these point-to-point networks, except we don't have a route for the 555 network. So R1 can get to the 555 network. We verified that, but R4 can't. Why? Well, one of the things that's happening behind the scenes is something called split horizon. Split horizon, as you may already know, says that when a route is received, in this case by R1 on serial 0/2, that interface, by default, it should not send the update back out the interface. Meaning if R4 tells R1 about the 444 network, R1 will not use that same interface to advertise the 444 network, even though it's going down through a different PVC down to R5. Because it's the same interface, it applies. Now, here's what catches a lot of people. If we did this on R1, let's go to R1 and do a show IP interface for serial 0/2. Now, right here, we have the split horizon right there. And what happens on frame relay on a physical interface, split horizon is disabled by default, which we would think, oh, that's no problem then. R4 can advertise its networks up into R1, and R1 can feed them back out because split horizon is disabled. Unfortunately, this only applies to RIP. And if we're running EIGRP, it's still enabled. Split horizon is still preventing the updates from coming in on serial 02 and out to R5. So to fix it, we would want to go into interface serial 0/2 right here. I'll point to it. We want to say no IP split horizon for EIGRP Autonomous System 1. Now that we've done that, R1's going to have a little communication with his two buddies out there, resyncing, and now he's willing to repeat information. So a moment ago, on R4 and R5, we did not have the routes. Let's go ahead and take a look. So there was our routing table a moment ago on R4. No route to the 5 network. And now if we do a show IP route just for EIGRP learned routes, now you'll notice that we also have the 5 network as well. So that was preventing, split horizon was preventing us from getting the update. From R5 getting the update from R4 and R4 getting an update from R5 because of the split horizon on this interface at the hub. A solution to this non-broadcast multi-access network nightmare is to do sub-interfaces that are point-to-point. We could have broken R4 into its own separate network and R5 into its own separate network, just as we did over here on the left-hand side. And then the whole issue with non-broadcast multi-access and split horizon goes away because we're using 2 separate logical interfaces, one for R4, one for R5. So now are we done? Well, almost. Let's do this. Show IP route. R4 has a route to the 5 network, and it looks beautiful. Check it out right here. So R4 says, yeah, I can get to the 555 network. My longest match is a 24-bit match, and my next hop is 23.1.2.129, which is R1. No problem there. And my exit interface is serial 00. So I should be able to ping it no problem. Take a look at this. Let's do a ping of 5.5.5.5. What's going on? I mean, we have it in our routing table. What's going on is this, is that R4 knows how to get to the 555 network. It forwards it to R1. R1 routes it down this PVC to R5, and it's there. The problem is that when R5 gets that packet, it's sourced from 130. And R5 doesn't have a route to get to the 130 address because it's on its frame relay multi-access network and it doesn't have a frame relay mapping for it. So it's R5's problem here that it can't return the packet. So let's go down to R5 and I'll show you what I mean. Show frame map. There's our frame relay mapping. And it says, R5 says, I know how to get to one specific IP address on the 23.1.128 subnet, and that's this guy because of the map. So if I want R5 to be able to respond to R4's serial interface, I need to add one more map. So here we go to our multi-point subinterface, and we're going to do a frame relay map for the IP address of 23.1.2.130. What I'm going to do is I want to use the HDLC 501 as an on-ramp to forward that, and I'm done. Now, I don't need to send the broadcast keyword on that one because I'm already sending a broadcast for routing updates up this PVC, and adding the broadcast keyword again would only cause router 1 to get 2 of my updates instead of 1 for every time I send an update with EIGRP. So you don't need a broadcast on non-directly connected neighbors on the same access and the same network. So if we do a look at our maps now, show frame map, we've got 2 mappings. We've got one that says I know how to get to the hub, and I've got another one that says I know how to get to 130. They're both using 501, but you have to have a layer 3 to layer 2 mapping to get to a device on that network, on a frame relay non-broadcast multi-access network. So now, we also ought to do one other thing. we also ought to do the same thing for R4 that has a mapping for R5's serial interface as well, in case he needs to ever source packets, or R5 wants to return a packet back to this IP address. We want to do the same thing on R4 and map a layer 2 to layer 3 mapping for R5's IP address. That was easy for me to say, right? So what we're going to do here on serial 00 is say to Mr. R4, dear Mr. R4, to get to the IP address of 23.1.2.131, go ahead and use your local DLC 401. And what that's going to cause, and I forgot frame relay, I forgot the keyword map. What that's going to do is going to cause R4, when he needs to forward a packet to this IP address, to stick it down the PVC this. It's going to show up at R1, who's going to look at it and route it back out the PVC here. So even though it's one logical layer 3 network, we are actually having R1 make a routing decision and forward it down the same interface, but a different del seed to get to R5. So now we're done. We should be able to ping. So now on R4, if we ping 5.5.5.5, that should work. And if we also ping 5.5.5.5, sourcing it from 4.4.4.4, which R4 owns, that one would have worked earlier. It's the interfaces that we had to return the packet to. And that's what we forget a lot of times too, is that in order for a ping to work, the packet has to get to the destination and the reply has to come back. So R5, in the first case, didn't have information on how to reach the .130, and we fixed it. So now if we save all these configs with a copy run start or WR, we now truly have full connectivity from every device and every network to every other device. So we go to R6 as a quick test and just do a show IP route. There's the full enchilada of every network that's reachable, and then we could test and verify that we have full reachability. I appreciate you walking through the troubleshooting exercise with me. We included verifying that the local router was okay, making sure the language of love between the router and the frame relay switch was solid. If that's solid, then we looked at the PVCs, which are labels of the permanent virtual circuit, and the mappings of what IP addresses are reachable through those local PVCs. And then once we have the PVC established and working, if we still can't reach remote networks behind our frame relay devices, we did show IP route and troubleshoot routing as well. Thanks again and have a great day.